between the zero doping and whatever doping you're at of this arc length.
What happens at zero doping then?
Yeah, so at zero doping, everything's particle hole symmetric. So as you adjust the magnetic field, the lambda levels move away from the chemical potential, and they never cross the chemical potential. And so you won't see this quantum oscillation. You still have these orbits, but they're just moving away from here symmetrically in a particle hole symmetric fashion. So you need the levels that keep crossing your chemical potential to see this quantum oscillation. Yeah, you need some finite doping, actually. Yeah.
Any other questions? In direct semimetals with fermions, there are two closed orbits that can form. One is only on the surface, the other one goes through the bulk.
Yeah.
So do you understand which will give rise to stronger quantum oscillations?
So that's dependent on probably many details. Like I would assume that the surface only has a shorter orbit, so there's less chance of scatter. That sounds a bit more robust to this order, but yeah.
On the surface, there's a kink where the two fermions connect, so it's hard to scatter from one to the other too.
So are you asking if you have this arc-like termination? So there's two possible terminations, right? One is where you have arcs, and one is where you have like a TI surface.
Yeah, so if you have the direct semimetal,
yeah. So this is
So then there are two fermions on each surface, and where they connect, generically there's a kink. It's not a smooth connection. So it's hard to hop from one fermion to the other on the surface, and it's also hard to go through the bulk. So I was just wondering which process.
Sorry, I don't understand why is it hard to go through the bulk?
Well, because there's the thickness. As the film gets thicker and thicker, it's harder to go through.
But it's not harder to go into it, right? If it's thicker, you may scatter before you get all the way through, but you always go into the bulk.
Yeah, that's what I meant. It's harder to go all the way through for thickness.
Yeah. Well, maybe we can discuss after. I'm not quite, I feel like I'm missing something important.
Yeah, so I want to follow up on that point there. When you look at the two, this is in the Dirac semi-metal, when you have the two arms. So it's like the plus and minus of one arc will then have to go through the bulk and come back. So, and then the negative and positive of the other one will make an opposite channel of circulation. So it's not like you'll go from one arc to the other arc on the surface, I think.
Right. You have two separate copies of this Y orbit in the ideal situation that don't talk to each other, basically. Yeah.
From surface to bulk back, circulating one way, and the other arc will be circulating the other way.
Yes, precisely. Yeah. Yes. Thank you.
So if while the system has finite doping, so the bulk, you have a bulk from the surface as well, right? So then once you're considering this quantum oscillation of the arc, the electron will go from firstly on the surface on the arc, then it will go to it's possible for this electron to go to the bulk Fermi surface. Then it's circling around the bulk Fermi surface, but it can circle for many times before it runs into the other surface.
Yeah, so I don't think this actually happens. So there's some topological connection between this bulk chiral Landau level and the surface arc, and the surface doesn't go into these non-chiral Landau levels, it goes straight into the bulk one.
Right.
So unless you scatter, this process where you kind of circle many times.
So the point is that if it circles many times, it's very difficult to estimate how much time it spends on this circling on the bulk Fermi. Okay.
But as I said, unless you have impurity scattering, this won't occur. You'll go straight through into this chiral mode instead.
Okay, if there's no more questions. Oh, there's one question in the back. Yeah.
You really have some well-defined connection between the surface arc and the bulk chiral lambda level, not the non-chiral one. It's related to Chief's question. So the bulk bands are well-defined in the clean. Okay, under ideal conditions in the clean case, or clean enough to see bulk quantum oscillations, you have these nice separate bulk lambda levels, and they're very well-defined. And just the chiral one connects to the surface states. The other ones can turn around just by scattering off the surface on their own. And you actually see exactly this if you just put this problem on a computer and find the exact eigenstates. So the semi-classic picture I gave was just the simplest way to understand it, but you can also confirm this directly numerically that this occurs.
Even with weak interactions, I guess.
Yeah, so interactions are probably not very important at low temperatures because the scattering rate for these electrons will go down at some kind of t-squared if you have some doping. So if you're cool enough, I think you can, and these are weakly correlated materials, so I think you can probably ignore dephasing from interactions.
Yeah, I think we have exhausted all the questions, so let's thank the speaker again. And we will reconvene here at 11.
Okay, thank you. I'd like to first thank the organizers for having me to give this talk. And so this is work that I did that when I was at the University of Toronto with Hae-Young Key and Eric, you just saw. I'm at the University of Waterloo now. And this is about a generic spin model of communidates, including some effects of kernel distortion. So today you've heard a lot about honeycomb iridates, so I'm going to go very, very quickly through my first sort of introductory slides. So we've seen this CADAD model a lot, and so I'm not going to try to convince you that it's interesting right now. And again, we know that these are built from these K-effective half states. You know, they're strongly spin-orbit entangled wave functions that, you know, give rise to interesting anisotropic physics. And again, there was this lovely proposal from Kelly and Galoon where they showed that if you had edge-shared octahedron and you only had oxygen-mediated popping, you could generate this coupling in a real solid-state system. One thing I just want to point out for future use is that when you do this, it comes out